Hi everyone, welcome to the lecture on electrodynamics. This is the 7th of the series, and again I'd like to mention our main reference, which is the Introduction to Electrodynamics by David J. Griffiths, and this book is highly recommended for you. I hope that one of these days you'll get a hold of this book. This is now the next chapter. We have finished the first one, and we're going to study about electrostatics. And our fundamental problem in this particular chapter is that we're going to solve the force, for example, of a distribution of charge exerted on a point charge or a test charge, for example. So in this case, in the figure, you have different electric charges here. You have here some charges. They're distributed discretely in space, and you have a test charge here, Q, capital Q. We call these one as the source charges. They give some the force. They give the force to the capital Q, charge capital Q. And so capital Q will experience a force out of these distribution of charge. So how will we do that? In general, the positions of the source charges are functions of time. The trajectory of the test particle then is to be calculated. In general, both the source charges and the test charge are in motion, but in this case, in electrostatics, we assume that they are at rest relative to each other. So in this case, we have a distribution of charge, source charges. We use the principle of superposition to be able to calculate the total force on Q. That means that you have to calculate each of the charges or each of the source charge, the force that it exerts on charge capital Q. You have to calculate each of them, and then when you're finished calculating them, you add them vectorially here. So when you have like 8 source charges, then you have 8 forces to add. So in basic physics, these forces are added by components in rectangular coordinates. So you get the x component, the y component, and the z component. Add all the x, add all the y, and add all the z components, and then you get the magnitude and then the direction of the total force. Here the F1, or the force F1, means that you determine the force on Q. You first compute with the charge Q1, and never mind, you ignore all the other charges. You just calculate the force of Q exerted by Q1 on capital Q, and then you go again, you do again to Q2, and similarly to Q3, and so on. So the total force on Q is just the sum of each of the forces due to the discrete charges. I mean, the discrete distribution of source charges. The force on Q depends on the separation distance between the charges. In general, it's also dependent on the velocities and on the acceleration of Q. But again, in this case, we're considering velocities to be 0 and of course acceleration to be 0. So for now, we'll just concentrate ourselves with electrostatics, which is a special case in which all the source charges are at rest relative to the test charge, capital Q. You know this before Coulomb's law. So what is the force on Q? A test charge Q will exert. So if there are 2-point charges separated by a distance scripted r here, the answer based on experiments is given by the Coulomb's law, which is written as this one here. You have the force is equal to 1 over 4 pi epsilon sub 0, where the epsilon sub 0 there is called the permittivity of free space. Of course, when you are not in vacuum, the vacuum, by the way, is also the free space. Where you're not in vacuum, the permittivity there is greater than epsilon sub O. So like, for example, if you have charges in dielectrics, or in, like, for example, if you have 2 charges immersed in water, so of course you're not gonna use epsilon sub O. Epsilon sub O is only used in vacuum space. So if you have 2 charges there, then the force would be equal to 1 over 4 pi epsilon sub O, small q times capital Q divided by the square of the distance between the 2 charges. And you have to multiply r hat because that's the direction of force. So if it's force on Q1 to Q2, then the r hat points from 1 to 2. If it's the force on Q2 exerted by Q1, then that would be r hat to 1, and r hat 1 2 is just equal to negative of r hat to 1. They're just in the opposite direction. By the way, the permittivity of free space is given by this value. Of course, this is determined by the Coulomb's experiment. Of course, the force is in coulombs. The distance r, or scripted r, is in meters and the charge should be in coulombs in the international system of units. The force is proportional to the product of the two charges and is inversely proportional to the square of the separation distance. That's what we know actually in basic physics. And of course, in this case, you have scripted r as the separation distance. Actually, when you have q, say q is here, and then you start from the origin. This is r prime, and you have q here, which is r. The separation distance between them is this one here. I'm sorry, this is opposite, should be opposite this one here. So that's r minus r prime. That's the separation distance, or the separation displacement, or the separation vector, I mean. So this is r minus r prime, and your scripted r is just equal to r minus r prime. And yeah, here. And the magnitude of r hat is just and the magnitude of the scripted vector r is just this one, and of course its direction would be r hat, scripted r hat, which is, this is the one here. The force points along the line from small q to capital Q. And by the way, the force is repulsive if the two charges have the same sign. Say for example, both are positive or both are negative, and they are attractive when the two charges have opposite signs. So you have here some problems. 12 equal charges Q are situated in the corners of a 12-sided polygon. What is the net force on the test charge at the center? So it's kind of trivial, but of course the solutions can, I mean, you can do the solutions for it. Now B, suppose one of the 12 Qs is removed, the one at 6 o'clock. What is the force Q? What is the force Q on Q? Explain your reasoning carefully. So how about if there are 13 charges? So you can also solve that. I mean, it's just superposition of vectors. So we now define what is electric field. Actually, when you have a charge, as I've always told my students before, when you have a charge in space, this charge actually radiates itself some electric field. It radiates electric field from itself. If it's a positive charge, by convention it radiates towards outside some electric field, but when it's a negative charge, then electric field would converge to that charge. So these electric fields are picked up by neighboring charges, like the test charge Q, capital Q. So it picks up and it senses that there are other charges in the neighborhood. So when the electric field is picked up by another charge, it will experience a force from the charge that is the source of the electric field. So if there are several point charges, Q1, Q2, and so on, at distances R1, scripted R1, scripted R2, and so on, from Q, the total force on Q would be this one, and then you can factor out Q, capital Q, over 4 pi epsilon, and then you have some terms left inside the parenthesis, and we define our electric field to be just the vector multiplied by the test charge. And so our electric field can now be written in this form, this one here. So electric field is denoted by E, and that is radiated by the source charges. So the electric field is a function of position r, because the separation vector depends on the location of the field point. And of course, it doesn't refer to Q, as we have said. We factor out Q from the electric field. We factor out Q to get the electric field from the force. And by the way, the electric field varies from point to point. So when you are near the source charges, the electric field you feel there in magnitude would be greater than when you're far away from the charge distribution, because the distance is it is a function of the distance. And so when you're nearer, you feel a greater electric field. When you're farther, you feel lesser electric field. And even from one point of the same distance to another point of the same distance would have different electric fields, because they may have the same distance from the source point, but if the direction of the line along the field points or the test charge is different, in different direction, then the direction would be different for the electric fields. So they may be just the same in magnitude, but the direction would be different. So more on the electric field. It is determined by the configuration of the charges, and E, or the electric field, is a function of R, is just the force per unit charge. And that would be, electric field is the field that would be exerted on a test charge located at field point P. What is an electric field really? An electric field is not visible, but it's there. You feel it when you're charged, you feel it. The field is a real physical entity that fills the space in the neighborhood of any electric charge. So we can just imagine electric field, we cannot see it. So here in this problem, find the electric field magnitude and direction a distance z above the midpoint between two equal charges q, a distance d apart, as shown in the figure. Check your result is consistent with what you expect when z is greater than d, and repeat part A, only this time make the right hand charge negative q instead of positive q. Anyway, this one here, this one here, you have P. So what Q would exert at this point here, what electric field Q exert on P, this Q here would exert like an electric field going there, and this Q would exert an electric field going here. So since they are the same in magnitude, the two vectors have the same magnitude as well but different directions. So in this case, you have a vector going here. It has an x component and a y component. Let's put the x and y component. So this is the x component, for example, just an example, and the y component would be here. The other force you have here, this one, and the components would be also in the x, which is this one, and the y would be this one for this other force. So in this case, as you look at the figure, these two forces will cancel because they're exactly in the opposite direction, and so you'll be left with the two forces in the y. So this is actually this is supposed to be the sum of the two forces. So that's it. By the way, it's also very important that you look at the symmetry of the problem, because it helps you calculate the quantities with much more speed. The logic is still the same, and it gives you, it saves you time to calculate. So exploit also the symmetry of the problem. So that's for, but how about if this one is negative instead of positive? So, or I mean, this is negative, this is negative instead of positive, then the force would be going here. because the direction r hat will be opposite. I mean, the direction of the electric field would now be opposite because of the negative sign. So in this case, what happens? The y component cancels and you only have the x component here. So this is now the electric field. So how about when the two charges are very far away from this point? When it is far away, what happens? The two charges would come closer to each other. So if they are, if P is very far, it would look at the 2Q to be just a single charge, and the total charge would be 2Q, and the point would be here if it's really far. But if this one is negative, then the charge here would be 0. But actually, there is an approximation of this in the future chapters. We call that multipole expansion, when P is actually far from distribution. There is a multipole expansion for the electric field, so it also gives an electric field. But in this case, if you look at this naively, you will say that the charge is 0, but actually it has a multipole expansion, which you will learn later on. But there are also other problems in electrostatics that does not deal with discrete distribution of charge. We also have continuous distribution. Some distribution would be line distribution, like here, and other distribution would be surface charge distribution. Like, for example, if you put a charge on a conducting sphere, the charge that you put on the conducting sphere, they will distribute itself on the surface of the sphere. And of course, in a material called dielectric, the charges are also distributed all throughout the volume. So you also have a volume charge distribution. But mostly in conducting materials, the charges would just settle on the surface of the conducting material, the excess charge. And in that surface, you will have a surface charge distribution. We usually denote the the line distribution, we denote by lambda. This is, of course, the charge per unit length. This is the small charge on a small length dl. And then you have for the surface charge distribution, you have sigma. This is the small charge per unit area, on a small area. And for volume charge density, you have tau, and this is just the small charge on a small volume. Sorry, this is rho and this is tau. So there are distributions lambda, sigma, and rho. So these things appear later on as we solve some problems. So for continuous charge distribution, the distribution of the charges now is not discrete. So your summation sign will be changed to an integral, and you now have to pick dq as the charge that would give out the electric field. So to sum this, you have to do the integral of dq. Of course, you have to put the direction of the electric field here, divided by scripted r square. If the charge is spread out along a line, you have a line distribution or a line charge density, and your lambda is just equal to dq over dl prime. You're dealing with dl, the prime coordinate, because this is the source. This is the source charge. So your dq will be lambda dl prime. So you have to replace dq here with lambda dl prime. So we can see that in the next slide. So you have to change dq with dl prime. So for surface charge density, your dq would just be sigma dA prime, and for volume charge density, this is rho d tau prime. So you have this one here for the line charge, and then for the surface charge you have this one, and for the volume charge you have this one. There's an important note here. The scripted r is the vector from dq, therefore that's from dl, dA, and d tau to the field point, because you will be measuring the electric field at a point away from the distribution of charge. So whether that point is near or far, that point should have a distance from the distribution, and the distance is a magnitude of the vector from the source distribution or the source charge to the field point. There's a warning here. The unit vector r, scripted r, is not constant. Its direction depends on the source point r prime, and hence it cannot be taken outside the integral. So you have to be very careful. You cannot take that out of the integral. So we'll now go to an example which is of course very familiar to you in basic physics. Find the electric field a distance z above the midpoint of a straight line segment of length 2L, which carries a uniform line charge lambda. So here you have a line charge. A line charge, and you're measuring the electric field at this point, P. So now, as I have discussed earlier, you have 2-point charges earlier, and you had that point charges exerting an electric field to a point P, and the direction of the electric field is just towards the y-axis. Like this one here, if you have a segment of length 2L, you can chop the length of the distribution, and then say, for example, if you're considering a DL here or a DQ here, you should also consider a DQ here by exploiting the symmetry of the figure or of the problem. So if you have here L and say this is X, then this is also X as well. And so if this one if this is your DQ, then that would exert an electric field going to here, and this one will exert an electric field going to there. And so we know that the X component will just cancel, so that your electric field is just going to this direction. So for two pairs of two pairs of DQ, which is distance, the same distance from the origin, which is at the middle of this line, will give you two electric fields that can cancel their X component and just give you a Y electric field. So if you choose another here, you should choose also a point, which is this one, so that it will also give you an electric field that points there. So how do we do that? So the net electric field of the pair is the electric field would be DE, this one. This is 2 times, because because the components, the Y components they add, or actually the Z component, we chose this axis to be Z, so the 2 Z components add, that's why you have a 2 here, and then you have a lambda dx. Instead of dl prime, you have dx because it's along the x-axis. The distribution is along the x-axis. This is over r square. And what is cosine theta here, by the way? Let's look at that. So theta is here. This is also theta. So what is this component? This is cosine theta of the electric field. But what is cosine theta, by the way? So this is, say, this is also theta as well. So this is cosine theta is equal to x over scripted r. This is the distance. This is also, the magnitude is also scripted r here. So cosine theta would be x over scripted r. I'm sorry for that. This is not x, this is sine. I'm talking about sine theta. For here, the cosine theta is actually z. The z here, because it's the p is z above the midpoint of a straight line, and theta is here and also here. So cosine theta is actually equal to z over scripted r. I'm sorry for the mistake earlier. And so what is r, by the way? What is r? So r, you can also compute that. You can also compute r, I mean the scripted r. The scripted r, this is a right triangle, this is z and x, so the scripted r would be z squared plus x squared, and the variable here is the x squared, and the z is just a constant, so you will be integrating with respect to x. So now our electric field will now look like this. So this is 2, the 2 is placed here beside lambda, but anyway you can take that out of the integral. 2 is a constant, so 2 lambda z, z over scripted r, which is this one. Of course, cosine theta is just z over z squared plus x squared raised to the 1/2, and you have dx here. And now the integral of this one would just be, by the way, the lambda, the z are constant, so you can take this all out of the integral that's here, and so you will just be left with an integral from 0 to L of dx over z squared plus x squared to the 3/2, and the integral of that would be this one. You evaluate from 0 to L, and that will give you this one here. And in this case you didn't include the direction because in the integral, because the z is just in one direction, it's in the z direction, and the z direction is a rectangular the z hat there is a rectangular coordinate, it's a rectangular unit vector, which is a constant, so you can take that out of the integral. So you will have E, of course, in the z direction here. So you will have E in the z direction of that expression. So if the point of the field point is very far away from the line charge, then z would dominate the denominator, so that your square root of z squared plus L squared, if z is very far away, then that would just be z. And so you will have an electric field that would look like this, very far away. So far away, the line looks like a point charge with charge 2 lambda times L. So Q This will be now the total charge of the line. Far away, you will see the line as a point if you're really far away from the distribution, and it has the total charge of Q, and so your electric field would reduce to Q over 4 pi epsilon sub O Z square. And this is just the electric field that was given by Coulomb's law. In the limit L going to infinity, that means your line charge distribution is very long, that extends to infinity, then the electric field would be here. The electric, if L extends to infinity, your Z square plus L square would be just equal to L, and this will cancel with the L here, so that your electric field is in this expression here. So if you have a long distribution of charge in a line, or if you are like a wire, for example, a very long wire, or even a small wire like a meter, but you're measuring the electric field very near the wire, it would seem like the wire is infinite on both sides, and so your electric field would just be 1 over 4 pi epsilon 2 lambda over S, where S there is the distance of the point to the wire. So how about this? Using the concept in the example, you can actually find the electric field also of electric field at a point P, which is distance Z above one end of a straight line segment L, which carries a uniform line charge lambda. So you can calculate that. Of course, there isn't any symmetry in this case, but check whether you can solve it or not. You also have this. In this case, you have a symmetry. You have a symmetry here, and you can use the result in the example. This one is very popular. This is a popular example which you might have experienced. So when you can calculate this example, you can find it in books, and or in Google. If you are able to find that, then you'll be able to find this, and if you're able to find this, you'll be able to find this one. So those are problems that you may or may not solve, but it would be very helpful if you solve them. So we have come to a point where we will have to discuss divergence and curl of electrostatic fields, but um, given the time, we will not be able to finish this in 10 minutes, so we will discuss this in the next lecture. So this is all for the 7th lecture, and we will discuss divergence and curl of electrostatic fields in the next one. So please study this lecture.